magnetic field lines. So similar to that of electric field lines, a slight difference is there. Actually, magnetic field lines always forms a closed loop because magnetic poles always exist in pairs, north south, north south. You will never find a isolated north pole, isolated south pole, because even a very small piece of magnet, it's a complete magnet with north south poles. So that's why magnetic field lines forms a closed loop. So I am showing the field lines of a bar magnet. Here is a bar magnet, and magnetic field, suppose this is north pole, this is south pole, then field lines looks like this. It looks like this in continuation. So you may draw several lines. Yeah, yeah. Then north to south, north to south. So field lines are nothing but it starts from positive and ends, I mean goes to south, that is north pole, and goes to south pole, and then continues through the body of the magnet from south to north. So it forms a closed loop. But in electrostatics, electric field lines, they never forms a closed loop. The reason is because positive charge, if you see this is negative charge, then field lines starts from positive and ends at negative. Starts from positive and ends at negative. Starts from positive and ends at negative. So, but in magnetic field lines, it is continuous. So north to south outside the body of the magnet, and then south to north. So it is not proper to say that magnetic field lines starts from north, because it is a closed loop. And if you have a closed loop, no one can say what is its starting point, what is its ending point. Can you say, if you have a circle, so what is the starting point of the circle? No one can say. What is the ending point of the circle? No one can say. So it is a customary that we assume magnetic field lines starts from north pole, goes to south pole, outside of the magnet, and then continues from south to north, and so it forms a closed loop. If you want to find the magnetic direction of net magnetic field, suppose at this point, if you want to know the direction of net magnetic field, then draw the tangent. This tangent will show the direction of magnetic field. So anywhere, if you draw it here also, then you can know the direction of magnetic field. If you draw the tangent here, then it will be along this direction. If you draw the tangent here, it will be along this direction. So this is the way to find net magnetic field, B, because it has two poles, no? North and south. So resultant field at this point is along this direction. So say at point P, along this direction. Magnetic field is along this direction. So the magnetic field is given by the tangent drawn on the field lines at any point. So direction of tangent shows the direction of magnetic field at that point. So we should learn some property of magnetic field lines. Now the first property is, now start writing. The first property is magnetic field lines or simply field lines forms a closed loop. Closed loop. The second property is the tangent drawn at any point on field lines merely shows the direction of magnetic field at that point. The direction of tangent direction of tangent drawn at any point, drawn at any point on the field lines, on the field lines merely shows the direction of merely shows the direction of magnetic field at that point, field at that point, and the next one is number 3. Magnetic field lines never intersect each other. They do not intersect each other. Field lines means magnetic field lines. We are talking about magnetic field lines. Field lines do not intersect each other. Sometimes this question comes in 2 marks in CBSE board. Why field lines do not intersect each other? Similar type of question has been asked in electrostatics also. Electric field lines do not intersect each other. So they never intersect each other. The reason is very simple. If they intersect, suppose you have a field lines along this direction, another one is along this direction, and they are intersecting at this point, then field lines at point P is this way. So if you draw the tangent along this curve, so this will go like this, and if you draw the tangent on this curve, this will go like this. So at a single point, then magnetic field will have 2 directions, whereas magnetic field and electric field at a given point has a unique direction, and that's why magnetic field lines will never intersect each other. Why? The answer you can write yourself. If they intersect, because you have to prove it by assuming the contradiction. So if they intersect, then from the point of intersect, one can draw 2 tangents along 2 different curves. And direction of tangent merely shows the direction of magnetic field. And at a given point, there should be one and only one direction of magnetic field. Whereas there will be 2 directions of magnetic field at the same point, which is totally absurd in physics. So that's why you can't say that field lines intersect each other. It is very much similar to the electric field lines do not intersect each other. Why? Can you write it? Okay. So this is third property. Now moving towards the fourth property. Now fourth property is we are writing the fourth one here only. So if the field lines are crowded in a region, crowding of field lines indicate the strength of magnetic field. I mean density of field lines. In other words, you can say density. If the field lines are closer apart, closer to each other, then density, density will be more, and then magnetic field will be more. So crowding of field lines in a region indicates the presence of strong magnetic field. And whereas if the lines of force are separated far apart, density is less, then that will indicate the presence of weak electric field. And if the field lines are separated through large distance, then this will indicate the presence of weak electric field, in that region, weak magnetic field in that region, So what I mean to say, if you observe magnetic field lines like this, and if I ask you, I will give you the 2 points. Suppose this is point X, this is point Y, and if you are asked to tell out of X and Y where the magnetic field intensity will be higher, so your answer will be magnetic field will be higher, magnetic field strength will be higher B at X. Obviously, it will be more than B at Y. Means the strength of magnetic field is measured by the field line density. More crowding means more strength of magnetic field. Less crowding means separation is large. It means magnetic field is weak there. So this is the fourth property, and this way many properties are there. So it will be better to learn a few more. And okay, should I rub this portion? Sneha, yeah. It will be good. So magnetic field lines, less density means field is weak, and more density means field is strong. So this is fourth property of magnetic field lines, and the next one is uniform magnetic field. In uniform magnetic field, now I am rubbing this portion. Uniform, write down the heading, uniform magnetic field. Uniform magnetic field. It is very much similar to the electric field. Only the difference lies it forms a closed loop. Magnetic field lines forms the closed loop, and electric field lines, they do not form the closed loop. The basic difference is a uniform magnetic field. Uniform magnetic field. A region is said to have a uniform magnetic field if magnetic field remains same in magnitude as well as in the direction. So a region is said to have uniform magnetic field if the field remains same. Field remains same in magnitude as well as in direction. At every point inside the region. At every point inside the region. So, how will you represent it? By drawing field lines. So, if this region is having uniform magnetic field, then field lines will be drawn like this: parallel, equidistant, unidirectional, straight one. This is representing uniform magnetic field. Uniform magnetic field. Magnetic field. So how will you represent it? By drawing parallel lines, straight, equidistant, unidirectional lines. So this is a pictorial representation of uniform magnetic field. If this room or if this region is having uniform magnetic field, it means field lines should be parallel, unidirectional, equispaced. Because if spacing here is less, spacing here is more, then field at this point will be more and field at this point will be less. Because crowding, I mean density, defines the strength of the field. So that's why uniform magnetic field is represented by this diagram. It means if you consider a point here x and suppose this point is y, then magnetic field at y x is equal to magnetic field at y. Everywhere, at all points, magnetic field should remain constant in magnitude as well as in direction. Okay, now the reason of magnetism. So let us see the atomic view of magnetism. Molecular theory and atomic view, two regions are there. So we are talking about the molecular view first and then atomic view. So each molecule of a substance material behaves as a tiny magnet. And molecular view, should I rub the whole board or okay? So yeah, it will be better. It will be better if you take the screenshot then, because I am going to change the topic. No problem. You can take. Okay. So we are talking about the molecular view. So this molecule behaves as a atomic and molecular and atomic views of magnetism. So why is substance shows magnetic property? Like you know, there are three categories of magnetic material that are diamagnetic, paramagnetic, and ferromagnetic. Actually, it depends on molecular theory. Suppose if you have a material and this material has so many domains like this, you can make it like this. And if the molecules, because each tiny molecule behaves as a magnet, so itself it is a magnet. This arrowhead is north and the tail is south. So you can draw so many north, south, north, south, north, south. And if all the tiny magnets are aligned in same direction, then it has a strong magnetization property. So this is all the tiny magnets are aligned in same direction. So this is the condition when a substance gets fully magnetized, like iron. After getting saturation, it's all the molecules are aligned along same direction. I mean, each molecule behaves as a tiny magnet. Each molecule behaves as a tiny magnet. Okay? But when it was not magnetized, in that condition, so in case you see before magnetization, the same domain, I'm making the same domain, some of the domain has like this, this may have like this, tiny magnets alignment, this may have this type of alignment, this may have this type of alignment, and this may have something like this type of alignment. So if the net dipole moment, remember dipole moment was a vector quantity, and that dipole moment, net dipole moment is 0, then this is the case when it was not magnetized. But when a magnetic field is applied, then its tiny magnet is getting aligned, and if all the tiny magnets are aligned in same direction, saturation, the substance requires saturation value, and then no more magnetization is possible. This is the case. Here magnetic dipole moment is not zero. But if it has net magnetic dipole moment zero, means the substance is not magnetized. It's a simple iron piece. And when it is put in a magnetic field, and if you keep on increasing the strength of magnetizing field, then the molecules, tiny magnets getting aligned, more and more magnetic tiny magnets are getting aligned, and then it has some net dipole moment, and then it behaves as a magnet. So this is the molecular view, molecular view, molecular view. So this is a case of magnet, and this is a simple iron piece, simple iron piece. Or you may have different types of material also, like copper, so which is a diamagnetic substance. In diamagnetic substance, the net dipole moment is zero. So now the atomic view is important because we are getting the microform. So atomic view, in atomic view, a substance like a atom consists of a positive nucleus. An electron keeps on revolving around it in circular orbit. So consider this electron. So electron, if it is moving in anticlockwise direction, then velocity will be along this direction with velocity v. And this electron has some time period because it completes one full revolution, say after time t. So that t is nothing but time period. So then time period of electron, time period, time taken by the electron to complete one full revolution around the nucleus. So that then time period t is given if t be the time period, let t be the time period, then r is the radius and v the velocity, then how will you find time period t? That is t is equal to circumference is 2 pi r if r is the radius. So what is the circumference of this circular path? That is 2 pi r. And we assume that the electron keeps on revolving with constant speed v. Then time required to complete one circular path, so that time t is equal to, not t, it is circumference, right? Circumference, or you may say distance, circumference. So then time period t is equal to 2 pi r divided by v. 2 pi r divided by v. Distance by speed gives you the time. And because electron is moving this way, so charged particle, electron being negatively charged particle is moving in anti-clockwise direction. So current will be in clockwise direction because current is opposite to the motion of electron. So if electron is revolving in anti-clockwise direction, the current will be in clockwise direction. And that current I is defined as charge flowing per unit time. Per unit time, Q by T is defined as current. So this I is equal to E divided by T is 2 pi R and then this V. So I current and then current is equal to EV by 2 pi R. At the same time, this magnetic dipole moment and Bohr's second postulates. In chemistry, you have studied, I think, in atomic structure or whatever chapter is there. So, angular momentum of revolving electron. So, if L be the angular momentum of electron revolving around nucleus, then L, this is MBR, moment of momentum. So if M be the mass of electron, then momentum is MB, and take the moment, that is mb into r. This gives you angular momentum, L, mbr. Okay. Then magnetic dipole moment, since it is a current carrying loop, because electron is moving in anti-clockwise direction, so current is moving along this direction. The direction of flow of current is along clockwise. So angular, that is magnetic dipole moment, M, which is magnetic dipole moment, and you have already studied about a current carrying loop behaves as a magnet. It's a dipole. One of the face acts as a north pole, and the opposite face will act as a south pole, depending upon clockwise and anti-clockwise rotation. So since the current is flowing in clockwise direction, the face which is towards the observer should be south, and the back of that will be north. So if it is a magnet, a tiny magnet, then dipole, then it must have some dipole moment. And dipole moment of a current carrying loop, we have already studied that M is equal to I into A. Yeah, that we have studied, I into A, in the previous chapter. So I is EV by 2 pi r, and then this A is pi r square. What is the area of the circular portion? That is pi r square. Now you can cancel this 2 with this r, then pi with this pi. So then EVR divided by 2 is the magnetic dipole moment. Now this you can substitute the value of VR. This VR is, this implies V into R L by M. Now let us replace this V into R is equal to E, and then L divided by 2, this 2 into M. Now M stands for, what does this M stand for? M is the mass of electron. M is the mass of electron, and this capital M is the magnetic dipole moment. So remember, in physics, symbols have their usual meaning. So this M for magnetic dipole moment, this M for mass of the electron, and L for angular momentum of the revolving electron, E for electronic charge. And you know, magnetic dipole moment is a vector quantity, and this L is also a vector quantity. So what should be the direction of M? Direction of M is, direction of M is given by, if the current carrying conductor, and if the current is flowing in clockwise direction, then the upper face is south and the back is north. So direction of current will be, direction of magnetic dipole moment has direction from south to north. Yeah, dipole moment, it's always from south to north. Similar to that in electrostatics, electrical dipole moment, minus q to plus q. Remember, for minus q here it is south pole, and for plus q here it is north pole. That's only the difference. So if you put a vector sign here, then this implies capital M is equal to EL divided by 2M. But before we put the vector sign, we must think about the direction of M and L. Whether the direction of M and L are equal, then it's okay. But if the direction of M and L are opposite, then one must follow a negative sign. So direction of dipole moment here is from south to north. The upper face is south and the bottom is north, and so this side is magnetic dipole moment. And angular momentum, which is R cross P. So R cross P means direction of R is this only, okay, and P, momentum, is along the tangent. Whatever is the direction of velocity, momentum will have the same direction. So momentum of this electron, revolving electron, is along this direction. So this is the direction of R, and this is the direction of P. Now rotate the vector R in the direction of vector P. R cross P. R cross P. So anti-clockwise. So if you rotate the cork in anti-clockwise direction, the cork will be advancing in upward. So magnetic dipole moment is that is angular momentum is along this direction. If the electron, this is the direction of current, and if the electron are revolving in anti-clockwise direction, so then this is angular momentum. Now angular momentum and magnetic dipole moment are just opposite. So then one must follow a negative sign. Here it has a negative sign, r cross p. So this is r vector, this is p vector, okay, momentum. Now r cross p, rotate it in along this way. So it is anti-clockwise. If you rotate anything in anti-clockwise direction, the cork will be advancing in upward direction. So this is the direction of magnetic dipole moment. And here is your, this is the angular momentum, and this is magnetic dipole moment. Since L and M are opposite to each other, that's why one of the expression will follow a negative sign. You write here, negative sign indicates that vector M and vector L are opposite to each other. Negative sign, you just write, negative sign indicates that M and vector L are opposite to each other, Now my question arises, if the electron here it is moving in anti-clockwise direction, if it starts revolving in clockwise direction, then also you have to put negative sign, or the negative sign will be abolished. You got my question? Take the screenshot, because I have to rub this portion, upper part. Okay. So if the electron starts revolving in clockwise direction, here it was revolving in anti-clockwise direction. Now imagine a scenario, if the electron is revolving in clockwise direction, then also we have to put the negative sign, or this negative sign is not required. Yeah, who can tell me? Who can tell me? Yeah. Now here the electron is revolving in anti-clockwise direction. Here the electron is revolving in anti-clockwise direction. But if the electron starts revolving in clockwise direction, then also you have to put this negative sign, or there need not to put a negative sign. Yeah. So voice Reha is, so that's your fault. So if the electron starts revolving, say, I'm making the diagram. Now electron starts revolving in clockwise direction. So then velocity will be along the tangent. This is electron mass m, and if the electron is revolving this way, then current will be opposite to this. So electron is revolving this way. Then dipole moment, see, so current will be opposite to this. It is clockwise, so current will be anti-clockwise. And if the current is anti-clockwise, then current will be in anti-clockwise direction. Okay. So if the current is in anti-clockwise direction, then the upper face will indicate north and the bottom will indicate south. Then dipole moment will be along this direction. Now think about that angular momentum. Angular momentum, which is r cross p. This is the direction of r vector. This is r vector. Now r vector is along this way and p vector is along this way. Now r cross p. So you are rotating it in clockwise direction. R cross p. This vector r is rotating in clockwise direction. So if you rotate r vector in the direction of p vector, it will be in clockwise direction. And if you rotate the cork of your bottle in clockwise direction, the cork will be advancing in downward direction. Am I clear to you? Yeah? Then also, your M and L are still opposite to each other. So this formula is valid in general. So M is equal to minus EL divided by 2 into M. Minus EL by 2M. So this is true. So whether it is revolving in clockwise or in anti-clockwise direction, in both the case the formula holds good. That M is equal to minus EL by 2M. Now once you know the atomic view, so what you learn, so every atom behaves as a tiny magnet. Every atom. So if you keep on dividing the magnet into smallest and the smallest part, the smallest part will be still a magnet because we cannot divide it beyond the atomic level. So that atom is itself a magnet. And that's why even a small piece, smallest piece of a magnet is itself a complete magnet, north-south, north-south. So one cannot separate north and south pole. You will always have the magnetic poles in pairs. You got my point? Yeah? Am I clear to you? Yeah. But in electrostatics, you may have isolated positive charge. In electrostatics, you may have isolated negative charge. So that scenario is a little bit different from this magnetism. Now, one small thing is there, Gauss law in magnetism. So very simple, Gauss law, B dot ds, since it forms a closed loop, and that's why B dot ds is always 0. Now, Sneha, okay, okay. Now I am writing that small Gauss law in magnetism. Gauss law in magnetism. So very simple statement, surface integral of it states that surface integral of magnetic field over any closed surface is always equal to 0. That is B dot ds is equal to 0. Now Gauss theorem in electrostatics, remember it? It was E dot ds is क्या था? E dot ds is equal to Q by epsilon naught. Now here no Q is there because if the surface bonds plus Q and minus Q, a dipole, then E dot ds will be 0 because net Q bounded will be 0. But here B dot ds is always 0. The reason is whenever you bound a magnet, because isolated poles can never exist. So whenever you bound a magnet, tiniest piece by a surface, then north and south poles are there, plus M minus M pole strength. So that sum is always 0. You cannot think about an isolated. If the isolated poles exist, then this Gauss theorem needs its modification. Then it will not be 0. Since magnetic poles always exist in pair, so B dot ds is 0. That is magnetic flux. Magnetic flux through a closed surface is always 0. Why I am telling like this? The total number of lines of force emitting from north pole will enter through south pole. So the number of lines of force emitting from some phase, the same number of lines of force should enter through the other phase. So net will be always zero. That is nothing but magnetic flux through a closed surface. It's always zero. It's Gauss law in magnetism. Okay. Now moving towards the most important topic of this unit is Earth's magnetism. That is in CBSE syllabus. These portions are nowadays abolished. Means for this year only, this portion has been abolished. Now, Earth's magnetism is very important for your CBSE exam, and so we should start Earth's magnetism portion. Okay. I'm writing here. Earth's magnetism. Magnetism. You know how the magnet was discovered? In 600 BC, Safford, you might have heard about this story. Safford in Greece, the small island called Magnesia. Their shoes, though the shoes were made up at that time of wooden, but some iron is maybe there, or some iron material is there. So the shoes get stuck with that place. And so Safford now becomes astonished why our shoes is getting stuck with this place. So then China started inventing this theory. So what is happening with that Safford? Why it is his or her shoes getting stuck with that place, so with that stone? So that was the early history of Earth's magnetism. So how it was discovered? Now after that, many magician uses that magnet piece or that stone piece to display some magic before the king, and king becomes pleased, and they award some thing to that magician. So then, many days after that, Earth's magnetism was revealed. The scientists they were trying to know the reason why Earth behaves as a magnet. So there are so many theories. The two important theories. The first one is, Earth is like this only. It's like a sphere, not exactly a sphere, but flattened in these two portions. So like shape of an apple. And this Earth is having, earlier theory was, there must be a magnet inside the Earth. Earlier people thought that there must be a bar magnet inside this one. Then only north and south poles will be there, and then one of this side will be north pole, other side will be south pole. But at the same time, the contradiction arises. So if there is a bar magnet, and magnetic material may be iron, nickel, cobalt, these things, ferromagnetic substance. And if it exists inside the Earth, and the temperature of center of Earth is more than 3000 degrees Celsius, core, mantle, crust. So core has temperature more than 3000 degrees Celsius. So anything in solid form cannot exist at that very high temperature inside the core or mantle. So the theory gets disproved because nothing will survive at this very high temperature. And at the same time, if you keep on heating a magnet, its magnetization is getting lost. Keep on heating. So if you increase the temperature of a magnet, its magnetization will be lost, because the molecular alignment gets disturbed and net dipole moment becomes zero. The moment the net dipole moment becomes zero, it will behave as a simple iron piece. So then this theory will be discarded, because if you consider a solid thing, solid like a magnet, bar magnet inside the Earth, then that solid will not exist in solid form, because at such a very high temperature, 3000 degrees Celsius, everything will be melted out. So it's not possible. Now then this theory will be abolished. Now the new theory starts that in the mantle of the core, liquid, metal in liquid form, hot magma, is revolving because Earth rotates about this axis, this is geometric axis, geographical axis, you may say. This is geographical north, this is geographical south. And Earth revolves east, west, along this direction, west to east. Its rotation about its axis is from west to east. So that hot liquid inside the mantle portion, that also keeps on revolving with the Earth. Because if Earth itself is revolving, that hot liquid will also keep on revolving in circular path. And now the question arises, if liquid is revolving, then why does it form current? That's not possible. Then which factor is responsible for the current in the core or mantle of the Earth? Now the liquid hot magma, I mean nickel, iron, cobalt in molten state. So because of the very high thermal energy, atoms of that iron, P or nickel or cobalt will lose electron. And then the left out atom becomes positive ions. And that positive ions in the liquid, that keeps on revolving in circular orbit, say along this orbit. It is revolving with the Earth. Since Earth is rotating about its axis, so liquid inside it is also rotating in circle. And that circular rotation of charge, that positive ions, from where do you get that positive ions? Because of very high temperature, the atom will lose electron. And that left out atom becomes positive ions. And that positive ions keeps on revolving in circular orbit. And if the positive ions are moving along this direction, the current will be along the same direction. So one may treat this as a current carrying loop. Current carrying loop. And a current carrying loop behaves as a magnet. Current carrying loops behaves as a magnet. So then one of the side will be south and other side will be north. So if you look the Earth from this side, this direction is clockwise. Okay. So this side will have south pole. So now assume this one as a magnet. Because though consideration of a bar magnet inside the Earth is a fictitious thing. And no one can assume a magnet inside the Earth. Because the temperature is very high. At such a very high temperature, nothing will remain in solid state. So just imagine you have a magnet here. No such magnet will lie. But just imagine for your concept. So imagine here is a magnet. Then what should be this face? This should be south. Why? Because this current is in the clockwise direction from this side. And so bottom side, it will be north, anti-clockwise. So from bottom side, it will be north. So actually this is not the magnetic south of the Earth. The reason is, you might have seen the compass. Okay, magnetic compass. How many of you have seen the magnetic compass? Many of you have seen magnetic compass? It's a tiny magnet, suspended, pivoted on a pointed edge. And this needle, which is a tiny magnet, can revolve in circular orbit like this. Revolve in circular orbit horizontally. Okay. You may have a magnet like this structure which can revolve in vertical orbit. Yeah. Possible? Why not? Actually, this is called dip needle. Dip needle. So this tiny magnet can revolve in vertical circle. But what you have seen in day-to-day life is a compass, magnetic compass, whose tiny magnet, which is pivoted on a point sharp edge, is keep on revolving in horizontal circle, like this, like this. Okay. So if you have a magnet that is magnetic compass and place it anywhere on the earth, their north pole will always points in the direction of magnetic field. If magnetic field is along this direction, the north pole will be along this direction. So remember, this is very important thing. North pole of a magnetic compass always points in the direction of magnetic field. Okay. So this is the orientation of a compass whose needle can revolve in horizontal circle. Okay. So if you bring a vertical compass whose needle can move in a vertical circle like this, then if you bring the compass here, then its north pole will point in vertically downward direction and south pole in vertically upward direction. If you are standing here, then you will find north pole of the dip, what you say, dip needle, that is the compass whose needle can revolve in vertical circle, like this. Then if you bring it here, then suppose this is north pole, the north pole comes like this, because north is getting attracted by the south. Okay. Since north pole is in vertically downward direction, so this pole here, the pole are magnetic. This pole is called magnetic north. Remember, this is magnetic north pole, and this is geographical north. North geographical. This is south geographical. South geographical. Okay, should I write SG? This is geographical north, and this is geographical south. Geographical south. At the same time, this NM will represent, this NM is representing, I am writing here, NM is magnetic north. If Earth is a magnet, then it must have magnetic north and south poles. So then it is magnetic north. And this, and if you bring the dip needle to this position, then north pole, I mean this north pole will be along this direction and south will be along this direction. Yeah. तो डाउनवर्ड डायरेक्शन में तो ये पोजीशन होगा साउथ. The needle will dip, the north pole will dip along this direction. So this is magnetic north and this will be magnetic south. So this is S. Should I write it as a SM? South magnetic. South magnetic. That is magnetic south. Magnetic south. So remember, this is actually true north. True north. Geographical north is also known as true north. And geographical south, true south. This is magnetic north, and this portion is magnetic south. So little bit confusing. You focus yourself. So which one is magnetic north? Which one is magnetic south? Forget about this portion. You forget this one. It's not required. Okay? Now magnetic field lines always starts, as I have told you, magnetic field lines starts from positive. Yeah, it starts from positive. If you have a magnet, here is a north, here is a south, then magnetic field lines starts from north, goes to south, and then continues from south to north. Same case this side also. So here is the scenario. In case of a bar magnet, magnetic field lines, it is assumed, customary, it's like this. So magnetic field lines starts from north, goes to south outside the body of the magnet, and then continues from south to north, then it forms a closed loop. But what you see here, the magnetic field lines of Earth is little bit different. Now, should I rub this portion? Okay. So okay, you just take the snapshot and I will rub this upper part and I will make the Earth again because many things have to be learned. Okay. Should I rub it? Have it? Okay. Okay. So this upper part is, I'm making the Earth once again to show you the direction of magnetic field lines of Earth. So this is the Earth. Here is your geometrical axis. I mean geographical axis, not geometrical. This axis is called geographical axis or geographic axis, about which Earth keeps on rotating. Okay? So this is axis of rotation also. Now, this side is magnetic north. Okay? So should I write NM? Magnetic north. And this side is magnetic south. So SM for magnetic south. This is geographical north. This is geographical south. Yeah? Clear? And magnetic field lines of Earth, actually you assume a bar magnet. And for this bar magnet, magnetic field lines start from north, goes to south. So if you draw the field lines of Earth, then it will go like this. So many lines. You can draw it. But remember, no lines should